Hello everyone. Today I am going to conduct a session on Module 2 of Mechanics of Composite Materials. Before that I am going to introduce myself. I am Kiran Kumar, Assistant Professor, PCT, Puttur. Yes, the Module 2 of Composites which deals with the micromechanical analysis of lamina. So which actually defines the lamina behavior in microscopic manner. Okay. So here we are going to study various mathematical aspects of the lamina. So whenever we want to talk about the lamina, there are composites are made up of, as you see from the figure, composite is made up of so many types of sheets, and these sheets is nothing but we call it as a lamina. And when laminas are added one over the other like this, so that this combination of the lamina will makes laminate. Okay, so that is the final product. So you got the difference between lamina and laminate. So this is what we call it lamina, and once lamina is being fabricated and they have been added one by one, and that gives you the laminates. So our interest is towards the lamina, that is the behavior of the lamina under different loading conditions. Okay, so in order to study uh, the lamina behavior, first we should know its the basic properties like the density, thermal coefficient of expansion. So many basic properties are there. So we want to study that. In order to study these things, uh, since we know that the composites is made up of fibers as well as matrix, we should know the contributions of these two to make the overall contribution to the composites. Okay. In order to study that, the slight mathematical expressions we are going to derive, that is we call it as volume fractions, because the volume of the composites is nothing but the combination of volume of fiber and volume of matrix. So how much proportionate it is, all these things we are going to study here. Okay. And to make a sense, let's consider a composite. Obviously, it is made up of fibers and matrix. And let us discuss about these things by introducing some notations related to the volume. Here, the V suffix C represents the volume of the composite, V suffix F represents volume of the fiber, and V suffix M represents volume of the matrix. And the next subsequent notations is density, related to the density. So density in terms of suffix C, F, M. Okay, and finally, when we want to make the relationship of the volume of composites to the volume of fiber and matrix, it is nothing but summation. Okay, so volume of composites is nothing but the volume of fiber plus volume of matrix. Okay, so that's what we have written here. So next, the simplification part that I can do is I will divide this volume of composites throughout these equations. Okay, if I divide that, so what is going to get? It is a ratio I'm going to get. That is VF, volume of fiber divided by volume of composites, volume of matrix divided by volume of composites. So that ratio we usually denote it by volume of, and we call it as volume fractions. That is capital VF and capital VM. So obviously that gives you unity. So this is what the volume fractions. You might ask questions like why volume fraction is required, because volume fractions are required to know the contribution of fibers as well as matrix. Maybe the 60% of fiber and 40% of matrix, or else 30% of fiber, remaining 70% is of matrix. Okay, so like this we usually go for fabrication process. Okay, that's why this volume fraction studying is much needed. Okay, next, I hope everyone understand this concept. So finally, you should differentiate between these two. V, small v represents volume of the composites, fibers and matrices respectively. Capital VF and capital VM represents volume fractions. It is nothing but the ratio of volume of fiber to volume of composites, and volume fraction of matrix is equal to volume of matrix divided by volume of composite. Okay, so that's what we are going to define. So it is nothing but the ratios: volume fraction of fiber, volume fraction of matrix. Now, in the same manner, I can get the relations by considering the mass fractions. Okay, so mass fraction is having a few more advantages compared to the volume, because when we fabricate any composites, it is difficult to measure the volume of either fiber or matrix. Matrix may be possible, but for a fiber consideration, mass volume calculation is very difficult. Okay, that's why in an alternative manner we can go for mass fractions. Okay, so let's see how the derivation goes on for this mass matrix. Let us. I'm going to consider the composite, which is made up of fiber and matrix, and we'll go through these notations. Okay, so you should not confuse these notations with the your basic notations that you adopted in the previous fluid mechanics problems. Okay, mass fraction or masses are denoted with the letter W. Okay, it's not your uh, new weight in case of the previous notation that you observed. So W refers the mass only. So let's look into this notations. W suffix C, F, M. As usual, W suffix C represents mass in composite, mass of fiber, mass of matrix. Okay. Obviously, when you consider masses also, it is nothing but the summation of the fiber. That is mass of the fiber. When you add it, the mass of matrix, that gives the mass of the composites. Okay. So this is a simple mathematics that we adopted. And as usual, we are going to divide the whole equation with the WC. That gives you a capital WF plus capital WM, that is equal to 1. So where this capital WF and capital WM represents mass fractions of fiber and matrix respectively. Okay. So this is what we are interested, WF and WM. So this finishes the both volume fractions and mass fractions of fiber and matrix. So with the help of these two, we are going to come across with the next derivation, that is the density in terms of volume fraction. Okay. So what is the density of the composites? That is a big question that will arise since it is a combination of fiber and matrix. Let us look into the. So in order to know that, let's go to the help of the mass of composites is nothing but the previous relations that we adopted. The mass of composites is nothing but mass of fiber plus mass of matrix, that is WC is equal to WF plus WM. Okay, let's call this as equation number 1. And next, we know that from our basic fluid mechanics properties, density is nothing but mass by volume. That is, in this case, mass we are represented by small w. So please aware of that. Mass is denoted by small w. So the density is equal to what right now? Or else density is equal to mass by volume, or else mass is equal to density into volume. So mass of composite is equal to density of composite multiplied by volume of composites. In the same way, that is true for the fibers also. That is WF is equal to rho F into VM. And similarly, WM is equal to rho M into VM. So let's call these three relations as equation number 2. Next is simplifications that we can do is substituting these values WC, WF, WM. It is nothing but mass fractions of fiber, composite and matrix into the equation number 1. If I am going to substitute these three relations into the equation number 1, so that we are going to get the equation of this form, that is density of composite multiplied by VC. In the same way, fiber as well as matrix. Next, we will divide the volume of composites throughout the equation, so the density of composites is equal to. So if I divide that, it gives you some ratios like Vf divided by Vc and Vm divided by Vc. So it is nothing but rho f into capital Vf plus rho m into capital Vm. So this denotes what? Density of composites is nothing but uh, density of fiber into the volume fraction of fiber plus density of matrix into volume of matrix. So sorry, volume fraction of matrix. So you should always note that Vf and Vm are nothing but volume fractions of fiber in matrix. That is capital Vf and capital Vm. So sometimes the previous equation is helpful. In the same way, as I told, it is much needed in terms of mass fractions also. Okay, let us look into the density of composites in terms of mass fractions. Okay, to derive this, we should go with the inverse method that we relate the volume relations. Okay, so that is capital Vf plus capital Vm is nothing but composites, volume of the composites. And similar to the previous one, we should look into the density of what we call each composition that gives you the equations of this form. WC, WF, and similarly for WM. So next what we can do is, I should substitute these values in terms of VC and VF and VM. So into the main equations. If it is VC, then what is the relation that we are going to get? It is WC divided by rho C, WF divided by rho F. Similarly, VM is equal to WM divided by rho M. Okay. So let's substitute all these terms into the main equation. Okay. So if I substitute, then it results into this one. It is nothing but a ratio that we are going to get. So once we got this, since we want the density, let's consider WC and divide WC throughout these equations. So if I divide that, so that I am going to get 1 divided by rho C is equal to WF divided by WC, WM divided by WC. So these two are nothing but volume fractions, mass fractions of the fibers as well as matrix. So that I can convert this ratio into the mass fractions of fiber and mass fractions of matrix. Okay, so that I got the relation of density of composite in terms of mass fractions and mass fractions as well as volume fractions. That is the previous one. Okay. Quickly, let us move on to the next subsequent relations that is much needed in micromechanical analysis. That is evaluation of the elastic moduli. So it is nothing but what? The elastic properties of composites that we want. In order to evaluate all these, which are all the elastic constants, the first question that we should ask ourselves, the elastic constants previously that we have seen for isotropic materials. Okay, so similarly, the Young's modulus as well as Poisson's ratios for composites also we need to find out. So let's look into these two terms. But since and what we call the composites is nothing but orthotropic materials. Okay, so that is it is not isotropic. The properties are not same in all directions. Okay, that's why we should find out the Young's modulus in different directions. Okay, so if I consider this figure itself here, since as we observed from the previous theories that fibers is having its maximum stiffness in the loading direction. Okay, so that is along the length of the fiber, and obviously the Young's modulus is also higher in this direction, that is longitudinal direction. In the same way, if I load it fiber in the transverse direction, then the deflections or the breakage of the fibers strength factors is very less when we look into the its transverse properties. So that's why we should calculate these elastic modulus in two directions. One is longitudinal directions, another one is transverse directions. Okay. Why this figure I have shown you here, because this one gives you the contribution of the maximum contribution of the fibers to the longitudinal strength. Okay. So that's why I should calculate longitudinal Young's modulus. So longitudinal Young's modulus is nothing but the Young's modulus in the direction of fibers. That's it. Okay. So in order to derive these relations, we should know we have to go through some of the assumptions. The first one is the bond between the fiber and matrix is perfect. Means complete load transfer should occur from matrix to fiber. And elastic moduli of the fibers are uniform. Obviously, it is required, and fibers are continuous and parallel. Means there will be a continuous uniform distribution of the fibers, and there should be parallel. Okay? It is talking about the uniformity of the fibers. Next, it should the fibers alone will obey the Hooke's law as well as the matrix. Okay, and the fiber possess uniform strength. So that is strength of each fiber should possess the uniform strength. And next one is composite is big of voids. So if voids are present, then this derivation is no longer valid. Okay. So by considering all these factors, let us look into the derivation part. First, in order to derive this, we should we should go through some of the models. Okay. So this is just a simple example of a model where the fibers are being oriented in direction 1, and 2 is the transverse direction. 1 is the direction of the fibers. Okay. In order to derive this, let us take only a small portion of the fiber, a single fiber, along with the matrix. Okay, where it represents that rectangular block which represents some of the dimensions as H represents its width, TC represents thickness of the composite, and LC represents length of the composites. Next, since we are interested in the contributions of the matrix as well as the fiber, let us denote its notations in this way. Okay, where TF represents thickness of the fiber and TM represents thickness of the matrix. So in this figure, I can easily say that thickness of the composites is nothing but thickness of the fiber plus thickness of the matrix. Okay. Next, under the loading condition, if I apply the load to the composites, then by using the first assumption that load should be carried by the matrix as well as fiber. Okay, so that's what given in terms of mathematical values. That is, FC represents the load on the composites, FF represents load on the fiber, and FM represents load on the matrix. And that's what given in equation number 1. The load carried by the composites is nothing but load carried, some portion carried by fiber, some portion carried by matrix. And by using our the previous strength of material equation, and similarly, force carried by fiber is equal to stress developed in the fiber multiplied by area of the fiber, and subsequently we will get the relations. for the matrix also. So Sm is equal to sigma m into Am. And we can also develop the relations of the force, stress with the strain. That is by using Hooke's law. Sigma c is nothing but E1 into epsilon c. So here you should note down that here the term E1 represents, E suffix 1 represents longitudinal Young's modulus. Okay, so the Young's modulus along the direction of 1. Okay, that's what it is denoted here. That's the relation 3a. Sigma c is equal to E1 into epsilon c. That is strain of the composite. Next, the relation for the fiber. Sigma s is equal to Ef into strain of the fiber. And the next for the matrix. Next, what we can do is we can substitute all these three equations into the equation number 2. So that and once I substitute those equations, later I can directly substitute those things into the equation number 1. So that I got the relations in this way. Stress into cross-sectional area. Here also stress into cross-sectional area of fiber, stress into cross-sectional area of matrix. So that's what we are going to get. Next, what simplification is necessary is I want the Young's modulus of the longitudinal Young's modulus. So that's why I will take the remaining portion, that is the strain of the composite as well as cross-sectional area, divide it into the equation number 4. Okay. Before doing that, let's go for the previous assumption. The assumption is like whatever the strain carried by the composites is equal to the strain of the fiber as well as strain of the matrix. That is, by using this relation, if the composite from this figure, if the composite is elongated in this direction, it is nothing but since the bonding exists between the fiber and the matrix are same, they are being deformed in the same magnitude. So we are going to take that method so that all the strains will be equal. That is, epsilon c is equal to epsilon f, that is equal to epsilon m. And the equation simplifies to in this way. In the same way, I am going to divide the whole thing into the composite cross-sectional area. Now, if you go through these two quantities, AF and AC, AM and AC, so I can multiply its length factor, okay, length of the fiber and length of the composite, both are equal, as well as length of the matrix and length of the composite. If I multiply the length factors, then it becomes Vf divided by Vc, Vm divided by Vc. So Vf divided by Vc and Vm divided by Vc is nothing but volume fraction. So that the final equation of the longitudinal Young's modulus E1 is equal to Ef into Vf plus Em into Vm. Okay, this is what we require in this derivation. That is what the longitudinal Young's modulus. So this you should always aware that the E1 is valid only in the direction of the fiber. So Young's modulus is applicable only load is applied in the direction 1. Okay, so that is what the meaning is. Okay, thank you all for this mechanics of composite material systems. Listening to my lecturing for 24 minutes. I hope everyone are at home. Please stay safe, stay at home.